We'll restart. I think 300 plus are there. I think we'll restart. Okay. Hope you can hear me. Yes.
Yes, sir.
Okay.
Yeah, please start.
So, like we planned, okay. So I can summarize. Okay. So let me use new notes. Okay. Right. For the new notes. What have we done so far? What we have done so far is we have done considered identical particles. Identical particles are considered. Okay. So these particles could be classically observed. Classically observed means we see them separately, like I can recognize them. That is a classical. It's called a Maxwell Boltzmann perception, or it's called a Maxwell Boltzmann distribution or statistics distribution. Okay, that is one way of seeing things, where particles are distinguishable. Most important, particles are distinguishable. Okay, and any number can occupy, any number can occupy any state. Any state. Okay, any number can occupy any state, right? So that is going to play a very, very vital role and gives a different distribution. Okay, the next one is Bose-Einstein statistics, where particles are indistinguishable. That is the most indistinguishable. Okay, and any number of particles in any state, doesn't matter. Okay, that is one. The other one is Fermi-Dirac statistics. Same identical particles, saying from different perspective. Okay, here particles are indistinguishable. Okay, and one particle per single state, single atomic state, single particle state. Okay, right? If I do that, I am getting different energies. I'll get different average energies. Average energies. Okay, different kind of average energies. So energy and particle average photon number, given how many number of particles there in the average energy. So there is all the numbers are different. Okay, and their corresponding partition functions also different. Z, 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 all are different. Okay, so in the first case, classical case, average energy is usually kBT. If there are n particles, multiply n kBT. Okay, right? So the number of particles not matters, because particles are distinguishable in a given state. I can see different kind of particles are there in it. Okay, only thing, much issuing thing is here in Fermi-Dirac and Bose-Einstein statistics. Okay, so in a Bose-Einstein statistics, right? So let me write down average mean number. Okay, mean number is equal to 1 by epsilon exponential, ER plus alpha plus or minus 1. So this is the expression for mean number. Mean number of particles in a gas, let's say ideal gas. Here I wrote two signs, plus sign and minus sign. The plus sign stands for Fermi-Dirac statistics. Minus sign stands for Bose-Einstein statistics. Okay, right? See the change. Okay, where remember alpha obtained by imposing overall number of particles is fixed. Okay, so that is the condition. Now n average mean number I know. Let's say I want to know what is the partition function for a given system. So partition function for a given system is not going to make a big fuss or big revelation in the case of Max Boltzmann. So I'm not worrying that much. So I'll worry only in the case of Fermi-Dirac and Bose-Einstein statistics. So the partition function, let me write down in the case of logarithmic, because partition function usually is very large. It goes very high. So we'll put a log, so it will slowly vary. So which is equal to alpha n plus or minus x summation over r. Okay, summation over r log of 1 plus or minus exponential minus beta er plus alpha plus okay. So let me restart my pen. Where is that? And does it goes to down? I'm not getting. Wait a minute. Is this one? No. This one? No. Okay. Maybe let me take a new one there. Okay. I shouldn't have crossed. Okay. So mean energies or mean number is exponential beta er plus alpha. Okay, I'll take nr plus or minus 1. Plus stands for Fermi-Dirac, minus stands for Bose-Einstein. And the partition function is alpha n plus or minus summation running over r log of 1 plus or minus exponential beta r plus alpha minus. Okay, summation close, right? So this is a partition function and the average number. Okay, now we'll try to see how these are like quantum statistics. The quantum statistics. Okay, seeing things from the quantum mechanics. Okay, now if I, and most important, the number is always fixed in both the case. Okay, if I let a number, the sum of the particles go any number, so BEC, so Bose-Einstein statistics, BES, would go to Planck statistics, photon statistics. Okay, as n infinity. Okay, and I am just saying infinity, and n can be unconstrained. Okay, so now specific cases. Okay, now let's take specific. Okay, specific cases. Let's say n is very small, means less dense, very diluted gas. Okay, n is small, and and then we will just change the temperature in that case. Okay, so what is the implication of n is small? Right now what I know, n average is summation over 1 exponential beta er plus alpha plus or minus 1. Now this is the one. So when n is very small, what I mean is I am summing of few terms to get the average. Now, so that means even I can sum various mean numbers for different states possible. Okay, what I mean is, so this is short form. Okay, even this is n. That means even these terms sum together should give me capital N. That means 1 by beta ER plus alpha must be very, very small. Okay, why? Because if I don't get this, the sum would go beyond n. So that is the case. I want to have these terms must be very, very small. When these terms are very, very small means what? Exponential beta ER, exponential beta ER. Okay, what is happening? Mhm. Mhm. Okay, let me take a app. The app is easier, I hope. I'm not getting. Where is my recent? Okay, so when n is small, I have a condition on. Okay, I have a condition on even the exponential term, so which has to be much, much larger one, so that 1 by e to the power of alpha beta er plus or minus is less than 1. Okay, right? Okay, so now that is one situation. Now let's say n is fixed to, let's say, small value, and I increase the t. Okay, t is large. The immediate impact when I increase the t is beta. Beta is 1 over Boltzmann constant into t. Na? So the moment I increase the t, beta would go to small. Okay, when beta is small, let's say beta tends to 0. When beta tends to 0, what happens? I have exponential beta multiplying onto ER plus alpha, right? Okay. So the beta tends to 0 means in order to have a contribution from the energy ER, I must have energies also very, very high values. High is required. So to have the product meaningful, okay, right? To contribute to the sum. So that means I have like the contributions are only possible if the systems are going to, the particles are going to occupy to higher energy states. Okay, right? So with that case, the average numbers would be less than 1. Okay, right? And what we see, the Fermi Dirac and Bose-Einstein statistics would actually come back to a simple scenario, right? So let's say n is small, t is large. Okay, so in that case, the contribution of 1 by exponential beta epsilon r plus alpha is much larger than 1. So 1 over exponential beta epsilon r plus alpha minus plus or minus 1 behaves like 1 by exponential beta r plus alpha, because this is not going to make any difference, addition of plus. So average number behaves like what? Exponential minus beta er. Okay, now I have to have a bracket. Okay, right? So let's send this exponential out. Exponential minus alpha exponential beta epsilon r. Okay, right? Fine. So as we know, even the average mean numbers also should satisfy sum to 1. Okay, so that means the sum r e beta epsilon must be sum to 1. Okay, let's take this out. Summation over r epsilon beta er is equal to n. So E alpha is n by epsilon e to the beta r plus sign. I'm sorry. Okay. And then if I have to have alpha, I'll send the log to the right. So I'll have log n by summation epsilon beta r. Okay. Right. So alpha, you know, the minus sign. Okay, then you can have nr exactly specifying n into exponential minus beta epsilon r. Okay, epsilon r divided by summation over epsilon minus beta er. Now even the alpha is exactly obtained with the Bose-Einstein statistics or Poisson Fermi-Dirac statistics. Okay, when if I raise the temperature, if you carefully see, this is a simple Max Boltzmann statistics. Okay, real scenario, na class that, like, say what is the average height of a class. What I'll do, I'll just sum all of the individual and then take right average in the same way. Okay, so I'm not seeing any plus minus sign here. That is Fermi-Dirac statistics or Bose-Einstein statistics dropping down to a conventional classical method. Okay, right? Now, when they raise the temperature, that is the scenario. When rise in temperature, what happens to the log z? That is the partition function. Let's see in that case. Partition function is equal to, okay, alpha n. Prevent this space from creating additional dialogues. Yeah. Okay. partition function alpha n. This we have derived 1 plus or minus, yeah, e to the power of minus alpha plus beta r. Yeah, this is the partition function. Okay, now we need to worry about the dependency of temperature. Okay, as we have known, okay, when rise in temperature, beta is going to reduce. That implies I need to have reasonable energies to get contribute to the summation. Okay, let's assume that that contribution is coming. Okay, right now, so in that case, exponential alpha plus beta er is much larger than 1. Okay, right? So that means what I can do in the log 1 plus or minus exponential alpha beta epsilon r case. Okay, what I can do, I can just expand this as this is much larger than 1, nah? Okay, so in that case what I can expand that and put it as 1 plus or minus exponential minus alpha plus beta. Okay, I'm sorry, this as the exponential, usually exponential x is 1 plus x and so on other terms, no? So that is what I'm trying to do. So I'm going to substitute this as 1 exponent 1 alpha beta epsilon r minus 1. Okay, right? So the minus sign and minus sign gets cancels. What I'm left with is log of some exponential. Sorry, exponential is missing. And log of exponential, actually I'll get alpha plus beta epsilon r. Okay, right? So now even the Planck, sorry, even the z which I have started with could be dropped down to z of Max Boltzmann divided by some n factorial. Okay, so why this is coming is the in the Maxwell Boltzmann scenario, means classical scenario, the particles are indistinguishable, and we'll see the things that if I interchange the particles, what happens? I would see like permutations are coming in, but in reality, quantum level, particles are you can't distinguish. Interchanging is not going to make. At the most, they can bring the symmetry. But in the Maxwell Boltzmann case, I have added counted accessible states more because of I am in a perception that things are distinguishable. So that's why the Fermi-Dirac partition function or Bose-Einstein partition function must be obtained from the Maxwell Boltzmann by removing that extra permutations which I have added by in a misconception that particles are distinguishable. Okay, so that is not the case. In this way, we can take care of the reality. Okay, right now, having studied all these things, now I know how to treat particles, whether they behave like a single integral spin or half integral spin. Okay, so I know how to treat them. If I'm not bothering about their spin, I'm saying things from the very outset, very far. Okay, so yeah, in that case, so how to apply to the real world scenario? That is, let's say your qubit scenario. That is what we want to see. So I see there is a question. When you assume exponential x much greater than 1, the argument has to be 1. How we neglect it in the expansion? Okay, so let me use I'm sorry. Yeah, let me answer the question how the expansions are actually. Okay, yeah, I hope this is the part you are asking for. Okay, right. Now what you have here is on the left hand side, on the corner, you have the average photon number, sorry, average particle number. It should sum to n. Okay, capital N, right? So that means each term inside the summation must be very small. Okay, right? So that means nr average is also to be small. Exponential alpha plus beta epsilon must be greater than 1, so that the fraction becomes much smaller than 1. Okay, so right, so that is the condition. Now when I increase the temperature, what happens? Beta goes very small. When beta goes very small, if I have any energy ERs contributing to the summation, okay, only when ER values are reasonably high, so that beta multiplying to smaller beta value, they are going to come into the picture. Okay, right? So in that scenario, exponential alpha plus beta epsilon are going to be very high. Okay, right? So in the Fermi Dirac scenario, exactly, so this is in general. Okay, right? So in Fermi Dirac scenario, right, when t is very large, the exponential is very high, higher than 1, not very high, just higher than 1. When it is higher than 1, I'll just ignore plus or minus 1 and then put the exponential to the numerator with a minus sign. Okay, so nr becomes exponential with a minus sign. Fine. So this is what I mean with a rise in the temperature. So with a rise in a temperature, the average number of particles, nr, mean number, would drops down to Maxwell-Boltzmann statistics. Okay, right? Fine. Yeah. So the x, what you are referring, it is a combination of beta ER plus alpha. So we should see from that prospect, not just a single x. Okay. Yeah, what you are saying, I think exponential x is much greater than 1. The argument has to be greater than 1. Does the mean for the particles that follow Fermi Dirac and Bose-Einstein statistics will have less number of states than those who follow the Max Boltzmann for a given number of particles forming a system? Is it correct? Okay. So what you are asking is comparison of all the three cases, right? Okay, do I have pen here? It is not writing. Okay, let me take a new sheet. Okay. So the question you are asking is about NR, which is usually beta ER plus alpha plus or minus this one. Nah? So plus sign stands for Fermi Dirac, minus stands for Bose-Einstein. Okay, right? So here, does the mean number of FD and BE statistics will have less number of states than those of the Maxwell-Boltzmann for a given number of particles. So for a Maxwell-Boltzmann, if you see mean number, let me have, okay. So Max-Boltzmann, okay. Where is my Maxwell-Boltzmann? I have it. This is generic case, number of particles, Fermi-Dirac, okay, Bose-Einstein, and Maxwell-Boltzmann case, yes. Okay, partition function I have. Okay, so this is the scenario. Okay, so ns is this. Okay, let me write that. So ns is n into exponential. I want to make the correct expression. Okay, yeah, EBS. Okay, EBS divided by summation over R into beta into ER. Okay, I hope I'm right. Yeah, right. So yes. Okay, so I want to compare all the three cases. Okay, now you see this is by default. If you see, this is at the most going to be less than or equal to 1. Okay, but this one can go larger, right? Okay, so obviously you can just comment ns max Boltzmann could be larger than ns either Fermi-Dirac or Bose-Einstein. Is that your statement? Yeah. So the number of states, yes, this is going to be less number of states. This is going to be large number. Looking at just comparing this with this. Okay, right? Yeah. I mean divided by a factorial n. Okay. Okay. So you mean to say here. No, remember. So the z with the factorial n, capital N multiplied is some like converted into this fashion. Okay, right? Okay, yeah, divided by n factorial. Correct. This is factorial n division is missing. Okay, yes, you're right. Yeah, correct. Okay, then now let's get back to where we left off with. Yeah, so we left off increasing Fermi-Dirac Bose. Okay, so yeah, here we stopped at this point. Okay, and Fermi-Dirac Bose-Einstein drops to Max Boltzmann, right? Okay, when temperature is high, remember, when temperature is high, right? There is one quote here, one statement I am making here. If n and t are such that we need to use Fermi-Dirac and Bose-Einstein statistics, then this the considered system of gas is known to have said to be generate. Means there may be a particle states with the same energy but different particle states. Okay, So that is what Fermi-Dirac and Bose-Einstein scenarios. Okay, if the system, the particles are strictly following Max Boltzmann, you can say there is no multiple states with the same energy, so non-degenerate. Okay, okay, that is when temperatures are very high. Fine. Okay, so then okay, this part we just saw, right? And yeah, this is a part I want to start with. Okay, okay, how many slides more? I have 15. So what I'll do, I'll use my lecture notes itself. Okay, so quantum state of a single particle. Okay, so how do I do? I just say this single particle can exist in state S with energy S. Okay, and I will also assume if there is some other particles also, single particle states around, and they are not interacting. That is easiest way to do. And when you want to bring in the interaction, we'll bring in that. So right now, let's say single particle classically, if I want to specify a location, I'll specify, and momentum I'll specify, and let's say it is confined to volume V. Okay, right? So but since I'm going to single particle level, I can say the particle is quantum in nature, means it shows a wave duality. Okay, duality nature, wave particle nature it shows. So I can associate a wave function. Wave function has got a wave nature. So wave function means waves. For the first thing comes to my mind when I say wave is electromagnetic wave. Okay, so electromagnetic waves would show propagating plane waves. Energy of that plane wave, just angular frequency multiply Planck's constant. Okay, propagation vector I can connect to momentum operator of that angular momentum, sorry, momentum operator of that particular particle. Okay, so using a de Broglie relation, I can show that momentum and wavelength of that are interconnected, inversely proportional. The moment I know momentum P, I can calculate energy of the system, because energy is P square by 2m. So I'm only talking about moving particle. Kinetic energy is there. Let's say it is not surrounded by any other particle. I'm not worried about the interaction. So the potential energy I'm not ignoring. Okay, so in that case, energy would be simply h square k square by 2m. Okay, so the complication would happen apart from interaction. I'll say the particles having some spin. In that case, I have to worry about the spin dynamics apart from translational dynamics. Translational dynamics means moving around. Okay, so energy I can write for a single particle. Okay, right? So let's say if there are any other particles around, those particles also fall into that kind of a momentum, so they can associate the same energy to those particles also. Okay, now the quantum wave function goes to zero at the boundary condition if the particle is confined in a particular cell or particle box. We saw that. So the moment you confine the quantum particle to the box, what happens? Things become quantized. It becomes a harmonic oscillator kind of a thing. So there is a energy states, energy values, all those things would come into the picture. Okay. Now, let's say I don't want that. I don't want to. I want to have a no confinement, but the wave which is propagating, let's say it has to satisfy some boundary conditions, obviously. Okay, so there is a forward propagating way, there is a negative propagating way, or there is a x propagating way, or y propagating way, z propagating way. So in those all the cases, if I want to capture here, so I want to show that the wave function should satisfy certain periodic boundary conditions, which is the particle is confined in the dimensional box of Lx, Ly, and Lz. So there I can write the plane wave boundary conditions like this. Okay, remember, I'm not enclosing. If the moment I enclose within a box, wave function should go to 0 at the boundary walls. I don't want that to happen. I want to have freely propagating, means the wave nature associated with that particle should expand to the infinity. That is what I want. I don't want to bring in any unnecessary boundary conditions. Okay, right? This is like you go into the like a big lake, right? You drop a stone, so the wave would propagate and keep on propagating for higher and higher distances. Okay, right? So now if you impose that kind of a boundary condition, okay, where waves are not deteriorated, are not dying out at the boundary, but still propagating, they may be doing a trough, like say they may just going beyond the boundary. In that case, there will be a condition like imposed on the propagation vector kx, ky, and kz. Okay, so what is that condition is kx at x plus lx is equal to kx into x plus some 2 pi into some integer. Okay, what I mean is wave is even going beyond the boundary. Okay, that is what, if I say wave is not going beyond the boundary, wave should reflect back. That is not happening. I want to let the wave go out, so that what I'm trying to do is I'm take a particle, I'm saying the particle is put in some place and it is having a space to expand or go around anywhere. So that is what I'm going to impose. The moment I impose, I can exactly find what is the propagation vector possible values, the x values, y values, and z values, which are simply 2 pi by L multiplied by some integral. Okay, integral values correspond to each dimension, nx for x dimension, ny for y dimension, nz for z dimension. Okay, right? Now, where n's can be positive or negative. Interestingly, there can be positive or negative integer values. Also, they can be 0. Okay, so I'll have a range of positive and negative and 0 as a integers. Okay, now having that, I can easily find what is the kr vector, the magnitude, and the moment if I know kr vector magnitude, I can also find what is the energy associated with such particles. Okay, energy associated with such particles depends on nx square, ny square, nz square, and also lx square, ly square, and lz square, where I'm presuming wave originated from that small box. I'm just presuming only wave is originated from small box. I'm not presuming that wave would reflect at the boundary of the box. It still propagates around. So that is what this kind of a meaning of a boundary conditions, periodic boundary conditions. Okay. Now the moment if I know energy, I can find how many such particles, how many dense of such particles could exist in a ideal gas. Okay, right? So this is this is like this is a number of translational states or a density of states exist for for particles with a propagation vector k to k plus delta r, some dr. Okay, right? So what I mean is, if I change the index number by small variation, delta nx, and same for y dimension, same for z dimension, if I just take a product, okay, what I'm going to get is I'm going to get how many number of particles and how many number of particles could generate a waves in that small domain. Okay, in this small domain. Okay, so and how many are there? The density rho of k is how many like the translational states are rising from a certain number of particles. Okay, right? So uh, where if I just divide it by this is actually density. If I divide it by volume, what I get, I'll get the number of particles per volume or number of translational states per volume. So which is actually comes out to be a constant. So right now, for a classical limit, what happens? We will just try to see. Okay, for a classical limit means what? Small n, large t. Okay, take the partition function as it is. Okay, right? Okay, where the psi eta, which is eta, I am saying. Okay, eta is what? Expo like a summing over exponential minus beta er. Okay, now just now I got my energy expression. Okay, that energy expression, if you substitute into the eta and substitute back eta into the log of z partition function, what you see is there are three quadratic terms contributing here. One is kx square, ky square, and kz square. Just like px square, py square, pz square, we saw in the case of classical harmonic oscillator. Okay, right? So that means you can easily compare this scenario to the classical harmonic oscillator case. Okay, so this is just a mathematical possibility of finding in the exact expression of eta. So you can just see it later. We are not going into detail. What matters for me is, okay, right? what is the average energy I am going to get for this particular scenario? Okay, average energy in this particular scenario is k beta multiplied by the total number n. Okay, right? So since I am talking in terms of 3 dimension, I have to add 3. Okay, and from each part, from each contribution, from each summation, I'm giving half k beta, right? Okay, so that is what I'm getting, half there. Fine. So average energy would be like this, and the this entropy would be, if you substitute average energy into the entropy expression, you would get that, the entropy expansion, where alpha naught, which I have showed you here, na? Alpha naught is actually obtained from the constraint of summation of number of particles should go to capital N. From there you can get alpha n, so which is here. Okay, right. Now the extinction. Now we saw a single particle which are not interacting, and let's say polyatomic case, when within a molecule there are two particles which are interacting. That is most important. That is what we were looking for in quantum computing. So in that case, how should I use whatever I understood so far? For example, we generated a partition function. How to use that here? Okay, so in the polyatomic case, for sure I have to write Hamiltonian of the entire system. Okay, Hamiltonian of the entire system consisting of two particles, for example diatomic molecule. So in that case there will be Hamiltonian contributions coming from various scenarios. So what I have listed here is, there is a translational motion. Okay, if I have two particles, where I have a picture somewhere. Okay, wait a minute. Okay, diatomic molecule, I have a picture. Yeah, here. So there two particles are there. I will have a center of mass at the center. I'll take the center of mass as a one particle to just study its translation motion. Okay, Rotational motion, if I want to study, I will assume either m1 is fixed and m2 is rotating about that, or m2 is fixed, m1 is rotating about that, or let's say center of mass is fixed, m1 and m2 are rotating about it. So these are the rotational dynamics possible. Another dynamics is m1 and m2 can come together and they go about. That's like vibrate. Okay, right? So the entire setup can move. That is a translation motion. One is fixed, other can rotate. Okay, right? That is a rotational dynamics, and are both can rotate about the center of mass. That is the center. Again, rotational dynamics. Another one is vibrational dynamics. Okay, and one more contribution comes from is okay. If you just take nucleus itself or electron itself, it rotates about itself. Okay, so in the case of nuclei rotates about itself. That is the intrinsic spin of the particle. It's not orbital spin. Orbital spin is captured in the case of ER-SR. Okay, right? In the case of HR, Hamiltonian rotational HR. But HE, what I'm referring here, is intrinsic spin. Okay. All right. Yeah. Sorry. ER is rotation of molecule about the center of mass. Okay. Right. Now, let's write down the eta for a given energies. Okay. Why I want eta is the partition function is actually eta to the power of n divided by n factorial. Okay, right? Why n factorial means I'm in distinguishability case, I count, let's say I have a figure for that also somewhere. Okay, wait a minute. Yeah, here. So if I just take a two particles, if they are distinguishable, let's say interchanging means I'm just rotating. Let's say B coming here means BA. Okay. So the same thing I can also get A coming this way and rotating in this direction. Okay. So in this way, translate like a change from here to here can happen in two ways. Okay, but the actual result is just interchanging. So that means I have counted twice, so I have to avoid that. I have to divide by that 2. So if there are n particles, I have to divide it by n factorial. Okay, yeah, fine. Now, having known the energy comes from all the 4 cases contributed. Okay, substitute that. When you substitute it, and if you see, there will be 4 different summations producted. Okay, so there are 4 different summations. Each stands for each contribution. And let's say you can say etas of translational, etas of electron moving around the nucleus, and ER, the nuclei itself is rotating about itself. Okay, EV would stands for vibration of 2 things. Okay, now let's worry about what is a translational Hamiltonian would look like. For a translational Hamiltonian, what I do, I say particle 1, particle 2 together. Moving means I can say that they're roughly fixed with each other with some distance, and the entire thing is moving. It is an approximation, by the way. In that case, I can treat both the particles are concentrated at the center, where the mass is m1 plus m2 is a center of mass perspective. In that case, what is the kinetic energy? Just a p square by 2 into the mass of the center of. Okay, so m1 plus I2 m2. The moment I know h, I can substitute this energy in the same format where P is converted into operator form. Okay, I'll get the energy. The moment I substitute the energy back in here, I'll get eta. Okay. So here it is a quadratic contribution is coming, right? The moment a quadratic contribution means you should always remember partition function will have a k beta t depending on what is multiplying on to that quadratic multiplication. Okay, so here quadratic term is multiplied by 1 over 2 into m1 plus m2. That also comes here. Okay, right? Gaussian integral. Okay, so and while in the integral case, I am actually integrating over certain volume element ranging from certain minus infinity to infinity for Q case, minus infinity to infinity for P case, and so on. All those things we are doing, right? So let's say all the entire integration would lead to some volume V. So that is actually captured here. Okay, and I will have a division by H. Yesterday we saw. So that is a three-dimensional situation. I have H to the power of 3. Okay. Now, okay. So let's apply this for electron motion contributing to the partition function. Okay. Right. So electron in the ground state, if I want to obtain what is the ground state of an electron, I can just take a Coulombic force of attraction, and from there I can derive what is the ground state of electron would look like. And if I just plot that, okay, that is a lot of study, so a lot of derivation is involved, so I am not going to do that. So what I am going to do, I am going to straight away take that ground state energy expression and plot it here. Okay, what you see here is very close to the nucleus, the energy is very high. Okay, as going away from the nucleus, energy becomes low, and as you go away from the nucleus, energy becomes high. So this is acts like some kind of a trap for the electron to stay in the ground state. Okay, so that is what uses the force of attraction traps the electron, right? So if that trap is removed, or the trap like electrons are somewhere here, so they may go out of the trap. So that is what happens. Okay, now let me call the magnitude of this ground state energy is minus of ed prime. Okay, right? So like a ground state energy is minus of ed prime at r equal to r naught. That is a nuclei to nuclei average nuclei to nuclei distance r naught I am just talking about. Okay, right? Now let's say if the energy of the surrounding, the thermal energy is much larger than the separation of the atom, sorry, electron from the ground to the excited state. In that case, what happens? Electrons were easily exited. Okay, so that is why we need to keep the temperatures so low. Okay, right? Or what we can do, we can have the excited states are farly placed than thermal energy. Means the thermal energy given is so small. In that case, electrons are trapped here. Okay, fine. So that is the condition I'm talking about here. Now let's take this energy, substitute back in the partition function. Okay, right? So the partition function, this kind of a partition function I'm talking about. Okay, when I substitute back, I also wants to bring in the degeneracy also. Okay, right? So degeneracy means there may be another possible ground state for the electron in the lattice. Okay, not only one particular location, it can also go somewhere and fall into that. So that case scenarios, I will call it as a degeneracy. How much degeneracy is there? Let's just call some omega naught. Let's say I don't know right now, so roughly I'll just put some omega naught. Okay, right? Now next thing, I know what is the contribution coming from the electron motion, the translation motion. The next thing I want to know, rotational part. Rotational part means if I just take mass m and mass 2, if they're rotating about each other or if they're rotating about the center of mass or anything, it is going to induce some uh, rotational dynamics. So when it comes to rotational dynamics, how to specify the rotational dynamics is by like specifying something called moment of inertia. Okay, so moment of inertia in rotational dynamics, it is just like an opposition exerted to the rotational dynamics. What I mean is, in say in translational dynamics, let's say I have a table. If I want to push a table, I have to put an energy, sorry, force equal to mass into acceleration, where mass of the table multiplied by some acceleration, which gives me some number. My force should be of that much. So who decides how much force I have to apply? The mass of the table, the opposition decides how much force I have to put. Same thing here in rotational dynamics. There is a opposition for the rotation to happen. What is that opposition? Is moment of inertia. So that moment of inertia is calculated by the reduced mass of the system. Okay, reduced mass is the reciprocal of m1 plus m2 by m into m1. So reduced mass comes out to be m1 into m2 divided by m1 plus m2. Okay, mass, reduced mass multiplied by, let's say the particles are separated by a distance r naught, so r naught square I have to multiply, okay, and divided by 2. So this is a simple classical mechanics formula for moment of inertia for a dumbbell. So there is a dumbbell. If I am just rotating a dumbbell, so that will have a moment of inertia is this. Okay, the moment I know the moment of inertia, I can go further. What further is, I want to calculate the energy. So energy is in this particular scenario, energy is its angular momentum to orbital angular momentum whole square divided by moment of inertia. Okay, what I mean is p square by 2m in the case of linear. Where did I have? Okay, okay, I don't have. Okay, let me use my hand note to explain what I mean. Okay. Okay. So if I have an object, if I want to push the object towards this distance with some acceleration, I have to apply a force which is equal to m into a. Okay. So m decides how much force. Okay. Which means, okay, let's say constant acceleration I'm talking about, which means m is a opposition. Okay. Same thing here. If I have something tied up, some mass, if I want to rotate, okay, if there is another mass here, m1, either if I want to rotate about the center of mass, I want to rotate. If I want to rotate this, it is going to put some opposition on me. What is that opposition? Is moment of inertia I, which is calculated by mu into r naught square, where r naught is the distance between. Okay, right? So say translation energy here, if it is moving with some momentum, so translation kinetic energy is this p square by 2m. Okay, same here, I will have rotational kinetic energy, which would be definitely, okay, so which would definitely moments moment of inertia in the denominator, okay, and also involves some angular uh, orbital uh, orbital angular momentum. Okay, so that is what I was showing here. h into j is an orbital angular momentum, where j is a quantum number, takes 0, 1, 2, 3, so on, square divided by 2. In place of m, I have moment of inertia. Very simple. Okay, so the j square here could be approximated as j into j plus 1. So in the orbital angular momentum case, that is what done. Okay, okay. So now I have the energy coming from rotational dynamics. So the moment I have rotational dynamics energy, I can put it into the partition function and get the exact partition function. Okay, why did I put a j square as j plus 1? I have explanation here. Okay, right? Usually for a given j, where a single j value, I'll have mj, the spin quantum numbers ranging from minus j to j with 0 inclusion. So how many mj's are I have? 2j plus 1. That's why I have a j into j plus 1 multiplied, put in the place of j square. Okay, right? Okay, so explicitly, if you get, okay, so what matters for me is when the temperatures are high, when temperatures are low or high. When the temperatures are very small, okay, this factor, which is exponential factor, is there, na? This factor which I have here, so temperatures are small means this factor is going to be much larger than 1. Okay, so means the rotational states do not contribute. Okay, only higher foot rotational states do not contribute. Only few rotational lower level rotationals are going to contribute for a very small temperature. Means temperature is going to make a huge role in the case of rotational dynamics. Now, if the T is very large, in that case, what happens? Okay, in that case, what happens? This entire factor with minus 1, V is going to be much less than 1. Okay, right? As I is not small inside, okay, what is the only possibility is spacing between the rotational energy levels would be very small. That is the only possibility. Okay, with compared to k beta t, right? Okay, so what I mean is j values are like the j values which I am going to take is very few, such that the energies are, these energies are spaced very close. Okay, right? Now if we can just find since the energies are so closely spaced, I can replace the summation, whatever summation I have here, for a larger temperature in terms of integration. When I do that, when I convert that into the integration, I can easily do a simple integration and get the partition function for the even this case. Okay, right? So that is what showed here. Okay, now that is done. For the vibrational dynamics, is there a way to get the partition function? Okay, already we know the lowest energy of the ground state electron, I know, and the potential energy, let's say U, right? So I can assume this, it is going to be a vibrational states of harmonic oscillator. The moment harmonic oscillator is there, I can get the harmonic oscillator energy as h omega n plus half, where omega is a vibrational angular frequency. Okay, so the moment I have energy, I can get the partition function. That is also straightforward. We have done that earlier. Okay, so this is how I can I can make some approximations and get partition function for polyatomic scenario. Okay, right? Which is coming with getting a contribution from translational motion motion of electron about the nuclei, rotation of a molecule about its center of mass, okay, and the vibrational motion of the individual atoms in the molecule, okay, right? So I have one more quick, okay, so, right. Okay, so so far we have talked about particles. What if I take photons? The one advantage for photons for me is photons are dual in nature. I can say photons are behaving like a particles. So anyway, photons shows a Bose-Einstein statistics. Okay, only advantage with photons is the overall number can be anything. So there is no alpha constraint coming in the average number. You see, okay, here. Fine. So photons are electromagnetic wave. They satisfy electromagnetic wave equation. Okay. And the solutions are just a plane waves. And the energy of the plane wave is h omega. And I can use that. I can get the even photons confined in a cavity, photonic based quantum chip. In that case, I can get the mean photon number and average photon number using the same statistical physics I can get. Okay, right? And when it comes to electron conduction, I can study using the Fermi-Dirac statistics. Okay, so for a finite temperature, I'll just go through the plot quickly. So Fermi-Dirac distribution has a Fermi function, which is just simply that 1 over exponential beta e plus 1. Okay, beta e is actually scaled with some factor mu, where mu is a alpha by beta. Okay, so what important for me here is for a finite temperature, Fermi function slowly decreases. Okay, for a lower temperature, Fermi functions suddenly drops. That is going to make a very crucial factor in the case of conduction. Okay, right? So let me take one question here. As Pauli exclusion principle does not apply for the particles following Bose-Einstein statistics, is it advantageous to use photons at low temperature for produce qubit in volumes than using other non-BE particles? Very good question. Okay, so right. Okay, so the photonic chips you are talking about, quantum photonic chips, right? Right. I think the experimentalist should comment on that because see, definitely see this material based quantum chips are need to be cooled, right? Okay, and the photonic chips, right? I think no need to be cooled, and the number of photons were involved there is few photons definitely. Okay, right. I think the my answer is definitely, yeah. I think yeah, definitely advantages, right? Okay, yeah, that's why the photonic based quantum computing is picking up, right? Okay, yeah. Any other question? Yeah, no other question. So let me summarize. Have like another 15 minutes. Okay, so I'll just use the canvas to summarize. Okay, so that it would be you would also know which one to use. Okay, okay. Let me enlarge this. Yeah, right. Okay, so I was asked to cover about what are bosons, what are fermions, okay, and how okay, there is one more question. How challenging to create qubits in volume millions and achieve low error rate in quantum computer can be explained in terms of statistical mechanics even when we could reach millikelvin temperature. Of course, yeah. Yes, definitely. Right. Statistical physics would definitely would help us to understand. Yeah, that's right. You're right. See, the errors coming because of the like say one thing is the mutual interactions. That is one problem. Okay, I presume like there are so many approximations I made. When it comes to reality, those approximations are not there. Because of that, what happens? I intend to do have some kind of a coherence in the system that is not going to be there. It is system is going to decoher at certain part. Okay, so that is going to add up as a noise. Okay, so right now, why we are in the noisy intermediate scale quantum, the systems are because of these things. The errors can happen in various ways. You intend to prepare the qubits at the ground state, but you will not able to prepare. And you intend to create a Hadamard gate using some internal photons or photon pulses. You will not able to create qubit like gates with perfection. All those things would contribute to the entire computation. That is what the errors are. Okay, these errors are definitely could be explained by up to certain extent using statistical physics, and people are studying on this. Okay, right. uh, See, errors from the environment means what? I cool the system to millikelvin. That was my perception. Okay, right? Due to some small trouble issues with that, let's say temperature slightly goes high from the millikelvin, that is going to shoot up the errors. Okay, right? So that is the problem there. Okay, so now you can see this is these are the like files from my folder. Okay, hope you can access my folders. So we started on 30th. Okay, Wednesday we started the Wednesday session. Okay, this is the second session. Wednesday, this is the first session. Wednesday first session. So I gave a motivation. Why do you have to study statistical physics? Okay, so the statistical physics, like we saw for the past 4 days, allows us to study particles, systems at a quantum level, then combine quantum things and make a classical. How it does that is the very, very beautiful thing is called partition function. Okay, so we have gone through several times the partition function. That is the key here. So partition function is a all-rounder. The moment you get that guy, he will give us average energy, average mean number, mean energy, and entropy, and even other factors like mean pressure. All those things are there. That is doesn't connect to quantum computing. That's why I did not touch that. Okay. So the motivation is partition function. Okay. The next session, the second part of it, I started. Okay, wait a minute. I started with what is a state? The state consisting of system particles interacting strongly or weakly. Okay, and the quantum mechanical description imposes uncertainty. Okay, right? And Schrodinger equation I can use, describe the system dynamics, and also get the evolution, which makes whatever description I have taken complete. Okay, So in the quantum case, few examples we took: electron revolving around, that is just like a harmonic oscillator. Okay, right? Quantum particle confined to a box. Here you see, and we got the energies for such boxes, such particles in a box. Okay, what is a classical quantum connection? We just checked how those things are connected. There is a boundary, how things we go either side, classical to quantum side, we can go, that we saw. Okay, and the collection of things are like called ensembles, right? And we even checked what are the thermodynamics laws. Okay, the most important thing is the energy remains constant of the system when it is not interacting with the surrounding. It varies when it is interacting. The entropy would always increase and becomes constant as time progress. Okay, and if I reduce the temperature to lower zero, the entropy is going to become constant, and entropy is not going to become zero. Okay, disorderness will be there and becomes a constant. Okay, so this is a 30th, and then 1st May, right? Let me see, what is this? Yeah, 1st May session, I gave a Gibbs principle. Okay, applying a Gibbs principle to harmonic oscillator, classical and quantum, and just to saw how their energies behave. Okay, and how it is possible is through partition function. Partition function can give mean energy, mean gas pressure, entropy, and even energy dispersion. Okay, right? So this is the case for 2nd day, and the 3rd day, let me see if this is the 1st half. Okay, this is additional material. Okay, Gibbs Boltzmann distribution. Okay, additional material. Let me take the running note. This is not running note, we are not going to go there. Yeah, this is what I want to know. 2nd May session. Okay, this 2nd May session we checked. Probably 1st, yeah, yes, 1st May session we did not touch. Okay, it looks like this one. This is what I was telling you earlier, harmonic oscillator, how energies are derived, explicitly showed here. Okay, fine. So if somebody has some doubts, you can just go through. There is something called creation and annihilation operators, which are actually momentum and position operator hybrid versions. Okay, E, Q, and P both were used to create annihilation operator and creation operator. Using that, I think I obtained the energy of a quantum harmonic oscillator. Okay, right? Okay, and yeah, and second, yeah, we just 3rd May is today, right? 3rd May sessions, 3rd May session A and B. This is the 1st half. In the 1st half, right? In the 1st half, we derived all the 4 cases, right? Max Boltzmann. Okay, so let me show you. Max Boltzmann. I have it here. Yeah, Max Boltzmann case, the average mean number, the mean particle number. Okay, and we derived Bose-Einstein. Inside the Bose-Einstein, there is a photon statistics where the numbers are not fixed, and Fermi-Dirac we derived. Okay, right? And all those 4 cases, or at least 3 cases, when I impose temperature constraint and the n constant, the capital N, the overall number. Okay, so if I impose that, I'll have a different scenarios. So that is the second half. Okay. Yeah, you see here. So I just summarized both FDS and BES into one equation. Okay, and even the partition function also FDS and BES into one equation. I'm not worried about Max Boltzmann distribution. I'm more worried about the actual scenario, the quantum scenario. That's why I took these two. Now I imposed the n is small and temperature is large. Okay, and beta is small. In that case, how Ft and B drops down to a simple Max Boltzmann, we saw that. Okay, beautiful. And now partition functions, if you see in the both FTS and BES case, again if you impose the same, partition function is actually dropping down to partition function of Max Boltzmann divided by n factorial. Okay, it's not exactly Max Boltzmann partition divided by n factorial, because here we assume things are indistinguishable. Okay, and whatever partition function I should get should capture that indistinguishability even after imposing the temperature. Okay, but in Maxwell-Boltzmann case, I started with distinguishability. I counted many times interchanging, so that's why the z is coming with the n factorial in the division here when I impose the classical limit of temperatures. Okay, so we applied whatever we learned for electrons, okay, within a lattice, right? And photons within a cavity. Electrons within a lattice, if I impose, what is happening here is, okay, Hamiltonian I have to divide into various cases: translation Hamiltonian, rotational Hamiltonian of the electron, okay, rotation of the molecule about the center of mass, okay, and vibrations of the molecule within, all those things. In fact, there are other Hamiltonians also comes. They may have very minute contributions, so they were actually ignored. Okay, so this is just an approximation. In that case, the moment if I know Hamiltonian, I can get the energies also. Having energy, I can get the partition function. Having partition function, I can find the other things like mean number and mean energy and so on. Okay, specifically how particular Hamiltonian or a particular energy contribution, whether it's coming from rotational dynamics or translational dynamics, okay, or vibrational dynamics, were also derived. Okay, explicitly I have not showed today. It takes some time. So what I suggest to you people, please go through my notes. It is neatly explained everything. Okay, right? Interesting thing is vibrational dynamics is described in terms of harmonic oscillator. Okay, right? And when it comes to photons, I use electromagnetic radiation description, where electromagnetic radiation means in general, if I confine within certain two walls, it goes and hits back and goes, it does rotation. It's like it creates a standing wave pattern. What I mean is, okay, so if I send a wave, it goes and hits back and comes back. This is one mode, okay, propagation vector of one kind. And let's say if it hits back and comes back, this is another propagation vector of one kind. Okay, so within a small volume, I can have so many of these things, so many of Ks, K1, K2. Why different K1s? This is lambdas are different, you see? Lambda 1, lambda 2. The moment lambdas are different, Ks are different. Ks are different, I can find how many Ks are possible and I can count them. So that is what I am going to do here. Okay. The moment I count them, I can get their energy density of that particular modes. So that comes out to be of this expression. Again, it itself would take a lot of time to explain. So you can go through it. It is nicely derived and you can understand. Okay, right? And the Fermi-Dirac statistics, how it can be used to understand electron conduction, also discussed very briefly. Okay, right? So that's about it. So I have covered all those things what is being asked as per the QT-02. Okay, if you want, I can quickly show you. Okay. This is QT-02. Yeah. So I was asked to cover statistical physics part. So I just slightly spill over a little bit other side. I discussed even Rabi problem little bit. Okay, so I did not go to rotating magnetic field case. Okay, so that is other case. So it's not in my domain, but I just touched it. But bosons and fermions we did discuss. Bosons are the particles with the integral spins, and fermions are the particles with the half integral spins. Okay, and the examples, electrons happen to be fermions, photons happen to be bosons in our qubit case. Okay, right? And they behave differently. To describe them, we need to have certain distributions, ensemble distributions. Those who are given by Bose, it's called Bose-Einstein distribution, and other one is given by Fermi-Dirac, so it's called Fermi-Dirac distributions. Okay, right? So a quick review of first and second law of thermodynamics we did do, and thermal equilibrium Gibbs principle. Thermal equilibrium means the system is confined, existed at some temperature T, not interacting with the environment. It's a thermal equilibrium. If such systems are there, what is the distribution which describes them? That is Gibbs distribution, that is Max Boltzmann distribution. We discussed, and applying that to classical and quantum harmonic oscillator, we have discussed. Okay, we saw how quantum can become a classical when I raise the temperature. Okay, and bosons and fermions and their quantum statistics we discussed in detail using a partition function, and Fermi Dirac and Bose-Einstein distributions with their applications to the real world scenario, like say electrons or photons, electrons confined in a certain location, photons confined in a cavity, also were touched. Okay, it is too much for 4 days time to cover, but I urge to you people to please go through all my hand notes which is being shared to understand more than what is in the book. Book few points like in between steps were missing, so those steps you can see in my lecture notes, you can understand. Okay, right? So that's from my end. Let me see if there is any questions. Okay, I think I have touched other questions what I have earlier. Okay, so I urge to all the faculties who wanted to get into the field, please go through it. It will definitely help a lot to get a better understanding instead of just taking things for granted. Let's say qubit means qubit, that's all. Or how qubit is in real world realized, whether it is realized from an electron, okay, or it is realized from a photon in a photonic chip, all those things you would give more appreciation if you know the statistical physics. Okay, right? So a canvas already occupied with all my lecture notes, right? First 30th April, 1st May, 2nd May, and 3rd May. Yeah, everything is there. So you are asked to please go through. Fine. I'll stop here.
Thank you very much, Ashwath sir. Thank you for the wonderful last total part on solid state physics was covered by Ashwath sir, and Parihar sir was there most of the time coordinating the events. In some time today we had exam, both myself and Maipal, we were there in our exam duty, respective exam duties. So Dr. Ashish has been doing a very great help. He is there. He is one of the joint principal coordinator from IIIT Jabalpur. Dr. Mustafizur Rahman also joined with us. Today we're just going to conclude. We'll spend some time, and most of you have enjoyed this QT-02, and you're also happy that the quiz is not there now. Anyway, we'll start tomorrow once the quiz questions come. Today's slides sir is uploading now, so you can go through the material, and he will share the questions. And then we will have that. Nivedita ma'am is also joining shortly, so we'll hope that she'll be able to there. And of course, many of our friends may watch this proceeding also. So yeah, you can pass on your comments on these things, and then if anybody is willing, we'll try to make you the host. You can share your thoughts and your learning, especially as the speakers are here. They would be happy to listen to you and understand, the way that they have been helpful. So we would like you to open up. So just the technical person is coming, and you can share. Meanwhile, I'll request a formal this thing to conclude. We'll conclude with vote of thanks towards the end. Before that, if any of you would like to share any thoughts, Dr. Ashwath will take some break. He has been teaching till now. So I'll just ask Dr. Mustafizur to share some of his thoughts and experiences. He can share. Dr. Ashish can also share his few thoughts. Nivedita ma'am will join. Later, we will give you a chance to speak. Some of the participants who have been regularly attending. I think most of you are here, 200 plus are here. So only you have been attending all the lectures, I would say. So what you say will matter to us. So and hence we will look at what you would like to say for us. So that's what we can look at. So maybe first Dr. Ashwath can go ahead. Sorry, Dr. Mustafizur can go ahead. Then we'll have Dr. Ashish speaking his own thoughts. Then by that time, if Nivedita ma'am joins, she will share. And then lastly, Dr. Ashwath will share. And some of your participants will give you time. We'll make you panelists so that you can speak. And then we'll conclude much before 6. We try to close it. One few announcements related to the quizzes. Don't worry about the quiz. We'll conduct all the quizzes for you. So presently, few of them are taking their retest. So that's what is happening. So we'll keep the quizzes open tomorrow. If some of you want to take quiz 1, quiz 2, quiz 3, quiz 4 also, or definitely quiz 3 and quiz 4 will be open. So you can take quiz 3 and quiz 4, no problem for the first time, right? If there are any issues, we'll sort out. So we are trying to look at trying to give you certificates on May 7th. We'll take the results till May 5th night. 6th, we'll try to prepare the certificates and all, and 7th, we'll try to distribute. Hopefully, if everything goes fine, at least to 700, 800 participants, we'll try to give the certificate. So all those who take exam tomorrow and on Monday. So by Monday evening, whoever takes exam, if all of you are able to take the exams, that's great. We will conclude. So around 800 certificates, I'm hopeful that we will try to release on 7th. If there is anybody who is left out, maybe another 15, 20 people may have left out one quiz or the other quiz, right? We'll try to help you trying to complete all those quizzes. And hopefully by 8th or 10th, we'll try to wind up giving you all the options. And maybe by that weekend, that Friday, 9th, we will try to give you the certificates. Right? One set of certificates, 800 odd, we'll release on 7th. So third and fourth quiz will be open till 5th. You can complete. If there's any other lapses that are there, we'll try to complete that and we'll try to look at, right? So Ashwath sir, can you take off one more screen so that the 4 of us will be there? Ms. Nivedita will be joining, so 5 of us will be there, right? So we can take a pic also. I'm talking to Jay Kumar also, he may also join. So let's. So over to Mustafizur Rahman from IBM.
Yeah, thank you, sir. First of all, I would like to thank a lot to Dr. Pilli sir, Professor Pilli sir. So I don't know how he is managing. Like this course is huge, I'm telling. So this many candidates are attending every day. Like there is a lecture and lots of quizzes, examinations, and all. And he has his like duties like in college in a big administrative position. I don't know. Like hats off you, sir, and the entire team of MNIT, I think, for organizing this course, and you all are spending a lot of time. So my contribution to this course is least minimum, I would say, because uh, Dr. Asad sir, Dr. Joy Kumar, Nivedita ma'am, all they are actually taking the giant portion of the course, and they have contributed most of the part. And I hope all you enjoyed this course. Uh, so just a small announcement, probably many of you just heard the news that IBM together with TCS and government of AP yesterday announced the machine coming to India, right? So it's a great news for us, like under the umbrella of National Quantum Mission, right? And so we are hoping like to get the quantum computer, largest quantum computer, 156 quantum computer in India very soon. And I hope that you are getting a lot of theoretical knowledge from Dr. Asad sir, Nivedita ma'am, Jay Kumar, and in the other QTs like QT-03 onwards also you'll be learning a lot about algorithms and programming stuff, right? And all this theory will help you to understand the stuff. And at a point, you will try to apply this kind of knowledge like that you are gathering from these basic subjects, right? Starting with the physics, quantum physics part, with the basics of quantum computing, slowly with classical and quantum algorithms, several mathematical analysis, and finally, the objective is those who are interested in the hardware, that is a different ball game, and some of you might be interested in the algorithm and application. So this is a good point of time to start and target some of the good problems, good research problems, right? So I hope you all enjoyed this course like QT-02, and many of you or most of you will be engaged in the next course QT-03, as well as you will also call your friends, colleagues to register for the next course. Dr. Pilli will announce shortly. So this is all about me, and let me know your feedback is extremely important, so that uh, so personally I learned a lot from this course MNIT. So I just followed a part of this course, and I thought like it's the best thing that MNIT is doing under National Quantum Mission for quantum education. This is all about from my side. Yeah.
Thank you so much, sir. Thank you for sharing. And it's a joy that you are here, sparing your busy schedule on working days. Actually, he was requesting for weekends, but because the schedule could not be there, sir spared his time. Yeah, all the participants would be happy to see Nivedita ma'am. I think most of the time the lectures, the camera was off. So some were asking me actually. So I said, yeah, we will have. So I think, so I'll request Nivedita ma'am to share a few words. Then we'll ask the participants to share their thoughts. Few words from your side. Yeah.
Yes, sir. Thank you so much, everyone, for like it's a wonderful feeling for me as well. I'm also glad that I was able to successfully complete my part, and I got a very good kind of feedback and participation from the participants' end. My topic was most of the topics were theoretical, and professor, sorry, not professor, even in IBM. So Dr. Rahman's course was like quantum information science and all that, but also was very theoretical. So I think it's a great joy to be here, and thank you so much. I hope to see you all either in one of the another panelists, just like here we have for QT-02, we have Dr. Jai Shankar with us, who taught the Qiskit part and the quantum programming part. I learned a lot, and the questions asked were amazing. A lot of questions asked were amazing, and it shows that participants are really interested into it. They are putting their heart into it. They want to learn quantum, which is a big thing and a big part of success from mine end as well as from EICT, and I guess so. And nothing to say more to Dr. Pillai and other members who organized this thing. Your help, your coordination with the participants as well as the panelists was absolutely worth mentioning. That is what I can say. Thank you, everyone. Thank you. Thank you so much.
Thank you, ma'am. And it's a joy that you were there. Since 2021, we have been associated, and two courses, most of the lectures were taken by Nivedita ma'am, and that's a joy. And it was a good time of learning. And I was following the chat messages that would go on while she's teaching, while Ashwath sir is teaching, or while Mustafizur sir is teaching. So the kind of interaction I really appreciated, all the participants, and the way that time to time it was more of a like a few people are sitting and we are discussing, like, and that's a great learning which happened. Maybe somebody who is watching the videos may not really enjoy the lecture, maybe because it's more of a conversation which is going on, and because whatever is going on the chat may not be visible for them. But then, yeah, a great deal of learning and clarifications have happened. And of course, we're going very slow, and I hope that we have covered most part of mathematics, most part of physics, which was needed, very much needed. These two courses, in one sense, they are compulsory courses in the minor degree. But of course, for our postgraduate diploma, you can take it further. And we are hoping that we'll try to put these lectures online and make it available as a course. And then we'll try to see how best we can offer you if somebody has missed these courses like QT-01, or somebody's missed QT-02, also some of your friends you have been asking. So we will provide those things, right? So that's what I was just waiting for Jay Kumar to join. He's on his way, but hopefully, yeah. Maybe if anybody of the participants are there, you can share your thoughts. If you can raise your hands, Dipesh ji will make you the panelist. You can just raise, so you can share few words. We will want to conclude by 6. So if there's anybody who would like to say something, if you raise your hands, we will, if you show your this thing, indicate, and then we will take you further. Anybody? You can place your you can also use the chat to read it, and then others are following. So yeah, the chats are going on anyway. Yeah. So yeah, I hope yeah. Yeah, Debanshu, you have been attending most of the sessions. You would like to say something? उनको बना दो देवांशु को. Yeah, Devanshu, you can unmute and speak. Please unmute and speak. We are not able to hear you, Devanshu. Yeah, there is some audio issue, I think. Devanshu, can you check? Yeah. Anybody else? Yeah, Mr. Baswaraj Patil, Dr. Baswaraj Patil.
Hello, sir.
Yeah, please go ahead.
Sir, it was really good to learn the new things for us as a teachers to deliberate the things. It's a new trend which is getting into the world of all the domains everywhere. I thank all the resource persons, Nivedita ma'am, Raman sir, and Ashwath sir for deliberating very excellent sessions. Especially, it looked like a handwritten where they are using the pads, which will be easy for us to understand the concepts. And the team coordination with you is very good, sir. It's a hats off for you to coordinate all the sessions from last one session. We are, this is second course we are going on. It's a very great task where we need to collaborate, address, and your responses in the chats are also very calmly answered, because we seen many unnecessary simple questions being a teachers being asked. It's a very polite way of handling you, sir. It's a great work. Thank you, sir.
Thank you. Srinivas को आया था. Raise करके. Okay. So yeah, we'll hear from, if you can raise your hands, we will make you a panelist and then you can take. Yeah, Anand, you would like to say something? Anand did his PhD with me, now working with NIIT University. Anand Kumar Mishra. Anyway, meanwhile, while we are adding them, those who are interested, we'll add them. I'll ask Dr. Ashish Parihar sir to say a few words. Then Ashwath sir also. Meanwhile, if Jay Kumar joins, we can conclude. Right? Anand, you'd like to say something? PCV Rao sir nahi the na. Okay, Dr. Ashish, you can go ahead, please.
Yeah, sir, can you please confirm? Am I audible?
Yes, sir. Yes, sir. Yeah, you are audible.
First of all, I would like to thank Pillai sir for giving me this opportunity to be just working as a joint coordinator with this FDP. It's a great mission towards the quantum computing, even the long. And I would also thank Mahipal sir for all the discussion and conversation and the coordination. And a special thanks to Mustafizur sir, Aswath sir, Nivedita ma'am for all the detailed explanation on these, quite complex topic. And even with the grace of these concept, even though as of now in our triple IT Jabalpur, there is no subject is being going on this quantum computing. But now I have proposed one subject on this quantum technology, and it will be going to be started from the next semester as well. So thank you so much, sir, for all of you, just working as a team to just guide and give your aspects toward this quantum technology to the participant. And I hope participant will also get some grateful insights within this topic. So I'm just ending up here. And again, I just want to thank to all of you for this beautiful sessions and this awesome FDP. And I hope, sir, Pillai sir, I think QT-03 is also going to be started from 16th of May, if I'm not wrong.
Yes, 16th of May, we have announced. So we will start from there. We will see some of the common faces.
Yeah, sure. Thank you, sir. Thank you.
Debanshu, you are audible now. Can you try? Debanshu, I think that there is some issue with your audio, I think. Debanshu, sir, can you check?
Yes, I think also that there is some audio issue.
Yeah, there is some audio issue actually from all sides. Yeah. Dr. Jaykumar Vaidyanathan is with us. So Yeah, sir, can you share few thoughts and advice to the participants? Yeah, they will listen more from you in QT-03 anyway. So, but then, yeah, you can share few words. And after him, we have one international participant, Masood from Bangladesh. Nasrullah ji, are you there? Hello? Yeah, you're there, right? So you're next after Dr. Jay Kumar speaks. You can share your thoughts. Yeah.
Good evening, sir. Am I audible?
Yes, yes.
Good evening, one and all present here. So it's my pleasure to talk with you in valedictory function. So whatever you learned in QT-01 and QT-02, you please go and revise if you have a doubt. More you go refine, more you clear your doubt, more you'll get stronger to upcoming next sessions. So this is what I suggest. So if you feel QT-01, QT-08 is somewhat tough, it is normal. Completely, you are in right track. Okay, nobody can understand in a single shot. Okay, so this is what my suggestion. So please go and revise whichever topic. If you feel more difficult, watch twice or thrice. Same video, same content.
Thank you. Thank you so much, sir.
Thank you, sir. Thank you.
Thank you. Thank you for joining. And this is the last session. May 16th onwards, we will have more from him. And we will learn more of programming and also simulations. So a lot of these content will come. Of course, there will be other speakers also who will be joining along with him, right? Yeah. Masood, we will listen from you. And then we'll conclude with Ashwath, sir.
Hello, am I audible to everyone?
Yes, yes.
At first, I will give a good round of applause for all of the speakers of our session, and I will definitely thanks to Pillai sir, for whom I get that opportunity to take that session. Actually, I am Nasrullah Masood. I am from Bangladesh, and whenever I saw the advertise on a LinkedIn profile, and that from that platform, whenever I saw that, I asked the question about can I participate in this course, and Pillai sir. And not only that, he paid my course fee also, because I didn't get that chance to pay the course fee. So I am very much indebted to him. I am very much grateful to him. And also, whatever I told in this case, that it's a very good mission, and especially National Quantum Mission. I am very much happy that from my neighboring country like India is getting much power in this case. And whenever this course started, especially from Nivedita madam, her lecture was very much attractive for me to start the foundation of this course. And also, MD Mustafizur Rahman sir, because I am from electrical engineering background, it was a very great experience for me to think that one communication system in a very different way, just like from classical domain to quantum domain. And also I will give thanks to Jai Kumar sir, because IBM Qiskit was not that much introductory for me. It was not well known for me, but after his lecture, I got that opportunity to play some child play with Qiskit, and now I think I am very much confident now that I will be able to get the quantum programming in a very professional way in very fast. And I am very much inspired from him, because he was also a student of QT, MNIT, and I will very much, I am giving thanks to MNIT Jaipur, because they are giving the opportunity to spread the quantum knowledge, quantum science knowledge among the whole countries. And just like a faculty, because faculties are very much closest to the students who will give the future leader of your country or somewhere in the world. So I am very much grateful to all of you, and especially the speakers, Pillai sir, and all the teams, that we will do a great nation, and we will build a future quantum world, and maybe MNIT Jaipur will lead in the future days. Thank you to all.
Thank you so much. Yeah, we tried to make the foreign currency payment. Actually, that was the sticking point, but the registration was not confirming. So I just, we said we'll do it later. We'll adjust, right? So I'm hopeful that we'll do that, right? Thank you so much, all of you, for joining. And I think we'll conclude with Ashwath sir sharing few thoughts. I think some Mohammad Iqbal is wanting to share. Mohammad Iqbal. Yeah. Yeah, Mohammad Iqbal ji, can you share your thoughts? Yeah. Mohammad Iqbal, you can speak now. You can unmute and speak. Okay, we can listen to him. Ashwath sir, can you share your thoughts and we can conclude?
Yeah. So, first and foremost, big thank you to Pillai sir for inviting us to be the part of this resource team. And I am privileged to be a part of this eminent resource team with Nivedita ji and JV and Mustafir, right? So I would be very glad to be there in that group. And so one suggestion or advice from my end is this AICT actually came up with an idea of not just progressing in the research, but also we should progress in the direction of studies as like understanding also. So with respect to quantum, and since they cannot do it in a shortcut, they wanted to do it systematically. They want to train the faculty to get the expertise in quantum computing, and they go and train the students. In that way, it is much more effective. So please contribute yourself for that objective uh, of being trained and then going and train the students. So it can't be shortcut. So the only way to train the students perfectly is possible only we train ourselves. So whatever we actually brought into these sessions, we like myself, I studied during my masters that time, so I had to get back and regain the things again. So it is possible. So only like JV was mentioning, things are not straightforward in a first attempt, right? It does requires a lot of practice and a lot of attention given to this particular topics. But you would really feel like happy, and you will appreciate once you understand the things, which is only possible by going through it once again. Okay, it is not like you just attended and left off there itself, because the target for this yourself also, you came into this FTP not just for the certificate, and also for get trained. So training is only possible if you practice, if you given one more attention to this. So I like other resource person, I also urge you people to please check back the material is being provided to you. In a way it is straightforward, no need to go anywhere and study and understand. It is given like a first hand information, so you can go through it. If there is any issues or anything, you are welcome to get back to us by mailing or by phone call or anything. We would be very happy to uh, clarify whatever things you have. Okay, so with that I conclude. So I urge you all to continue it, not just leave it at this point. Thank you.
Yeah, just adding one sentence, sir, taking your permission, right? Oh, so I thought my colleague Venkat is not here, just to adding his sentence on his behalf, hopefully. So, so if you see, like the objective of AICT is to build the manpower, right? And it is really, really required. So when we post like advertisement globally, even from IBM Quantum side and other industries, I hope the same case will be. And so any advertisement for a position, so it's not only the only software skills, it is not only the physics skill or the mathematics skills, it's combined of multiple skills. And it is only India where we find candidates. Even when we advertise globally, still we find the maximum number of candidates from India. So it's good. And India is like right now, it's a huge, like 140 crore, right? And the National Quantum Mission is a great, like a great effort in that direction. And those, especially the faculty members, I would request you to kindly start similar courses in your college as soon as possible, and please build manpower so that more industries come in India and more people are hired, and like it's a national quantum ready nation for the future generations. Yeah.
One clarification, sorry, thank you for the comments, Mustafizur sir. Regarding a few questions that were there, quiz 2 and quiz 1, a few of the participants started and they stopped there. They had some internet issue or something, so they scored less than 4 marks. So we opened it for only those people. So they are taking the second attempt. And we are permitting that. So I have written in the group also. So that's why the quiz marks are not visible. We have a copy of all the marks, so don't worry. Anytime you want, I can tell you what marks you got, so don't worry about that. One question from quiz 1 and one question from quiz 2 will be added for the second quiz. That is, the value will be 12. I think Jay Kumar sir has said that he ran the code again and saw that, and then he said, okay, let's give marks to 12. So we're giving, for the correct answer is 12. For those attendance constraints is one issue. So I've always mentioned that the requirement is on performance in the quiz. Attendance is what we have been compromising. I mean, we have been kind of ignoring because we hope that we have given the material, we have given the slides, we have given the videos. So you will listen to the videos at your free time and write the exams. So that way, most of you are doing, you're scoring well. So we will not be very stringent on attendance, as I know most of you are from industry. So I think we will conclude with, I think, Ist Vibhu or Iqbal, if both of them can speak, and we'll conclude with Maipal giving the vote of thanks. Thank you. Ist Vibhu.
Yeah. Am I audible?
Yes, yeah, you're on.
Yeah, thank you. Thanks for giving me a chance to speak. And we were connected and learning quantum computing since 2016 from the physics side. Actually, I started learning quantum optics. I want to give 3 points of appreciation. I don't think I ever missed any FDP course on quantum computing ever. Perhaps in 2021, Dr. Pillai had given one FDP, and I was a participant there also. So perhaps I know a bit of the things happening there. First, I have not seen such a prompt reply in logistics. I have never seen in any FDP. I have seen, I put my queries, I saw my fellow participants putting queries, and these were being replied then and there. I was so amazed by that. I have 20 years of experience in this academia, and I have never seen such a prompt reply. So salute to Dr. Pillai and the team. Second thing, usually FDP becomes monotonous. They are just a part of routine. They become a part of routine, flipping of PowerPoint slides which contain routine materials. I am from physics side. I have seen Dr. Nivedita working so hard in physics. She has elaborated basic quantum physics, transition from classical physics to quantum physics so nicely. The linear algebra part, I was so happy. I was listening this with my colleague whenever I got a chance, because we were taking practical classes together, and we were so happy that this person who is still doing PhD and so nicely explaining the things. So appreciation, please accept my appreciation, even from my colleagues to the speakers, that they have worked really a lot before coming. Ye homework we never see from speakers now. They present the routine materials. I saw a freshness in presentation of the speakers. This is quite appreciable. Please convey this to all the panelists. Third thing, well-structured syllabus. Well-structured syllabus. This division in 6 segments and elaborate syllabus of each segment, and that sticking of the speaker to the syllabus and finishing it to neck was really super. I have not noticed it in many classes I have seen. I have been part of these DPs and the pressure course as participant somewhere as speaker, and I have never found that people are so finicky about finishing this syllabus. That is amazing. So these 3 points are amazing about this. I salute all the members of the panel and the organizing committee for this. That's my point, and I would love to finish all the 6 courses. Though I am from 7 a.m. to this time, I was in my forest to organize this PUG exam. But meanwhile, I was listening because I cannot do anything, but I have to go through this recording. So I'm very happy. Please accept my appreciation. Thank you.
Thank you. Thank you. I think Nivedita ma'am wanted to say something. Yeah.
Yes, thank you. Thank you everyone for such kind words. Just one thing after Dr. Ashwath mentioned, I just want to highlight a bit of a different topic than just we discussed. That is, he mentioned that it has to be very structured and has to be very slow. Now, one problem I also have seen during the transition when I like there was a transition, I joined PwC and all. So I've seen, and in other industries as well, there is a like kind of a hurry. Everyone wants to do something with quantum. Now that is very good, but what's the challenge there is that they're lacking the real knowledge there. It's so niche, and see, any idea here is kind of, if it is your brainchild, so protect your idea, protect your thought, dig more, and don't jump over multiple things. It's not like an Android application that you have to develop a first an application, then only you can see or tag yourself that yes, you are a quantum developer. Please don't do that. I have seen this problem, and ultimately it is at the end of the day, it is going to affect you. Do not do that. Dig more and more, because quantum is so huge. You always remember one thing, that you cannot know at any point of time, you cannot know quantum fully. It is not at all possible. So the more you question, the more you get the clarity. But before you speak of something, just do as much research as possible. A lot of words are there, a lot of you will find a lot of such courses, and you just do a course and do some coding, and don't think that after that you know it. Seriously, honestly, and there is a huge amount of challenge there that you are going to face otherwise. So as Dr. Ashok mentioned, that there is no shortcut, and in quantum there is definitely no shortcut. So I just want to highlight this thing. Yes, and this is from a true experience. I faced this thing, so that is why I'm telling. Thank you.
Thank you. Thank you, ma'am. I think Mohammad Iqbal and then Dr. Mahipal will conclude with that. Yeah. One minute, please. Thank you.
Hello, am I audible, sir?
Yes.
First of all, I would like to thank everyone involved with this wonderful workshop on quantum computing, from the organizers to panelists to the resource persons. Today we were busy with the arrangements of the NEET, which is scheduled tomorrow, so we couldn't attend today's lecture to the full of the spirit. So sorry for that. I would like to say certain words, especially at the time of registration. When I registered for this workshop, I was not expecting that kind of workshop, the wonderful workshop it proved to be. So I thought that it will be a general workshop about what is a qubit, what are different quantum gates, and like that, and then there will be some programs on the Qiskit. But now, after completing this wonderful workshop, the kind of arrangement, the structure of this has been wonderful, and the in-depth topic is covered, especially by the Navidita ma'am. I was totally impressed by her knowledge and the way she explains different and the difficult concepts in a lucid manner. It was wonderful, not only about the quantum computing concepts, but I'm from the computer science field. Some of the topics related to computer science, like the computational complexity, they have been wonderful. She has explained them in a very beautiful manner. Thank you, ma'am, for that. And moreover, the other resource persons, especially the Mustafizur sir and Jay sir, and they have been wonderful. And it has been a wonderful workshop. It has added a lot to our knowledge. I was not knowing that much about this quantum world. Now I have been much more motivated towards this quantum world, and hope in future I will do my research work in this field. Thank you, everyone. Thank you, sir, for this wonderful workshop. And hope we will join the QT3 as well to increase our knowledge in this field.
Right.
Thank you, sir.
Thank you. Thank you so much. Yeah, over to Dr. Maipal.
Good evening to all. As we come to the conclusion of the enriching 20-day journey into the foundations of quantum technologies, it is my privilege and honor to deliver the vote of thanks on behalf of the organizing team at MNIT Jaipur and EICT Academy. First and foremost, I express my heartfelt gratitude to Professor Narayan Prasad Padi, Director MNIT Jaipur and Chairman EICT Academy, for his visionary leadership and unwavering support that made this program possible. I extend my sincere thanks to Professor Vineet Sahula, Chief Investigator, EICT Academy, for his strategic guidance and encouragement throughout the planning and execution of this initiative. A special word of appreciation to Dr. Emmanuel S. Pilli, Principal Coordinator of QT-02 and Co-Chief Investigator EICT Academy, for his active involvement, continuous mentorship, and dedicated support. I would also like to add that I have observed that every time, whatever task is there, right, Pilli sir always not only solves that particular task, but always look for the excellent, the best solution for it, and that was reflected in the overall coordination of this particular FDP. And we expect the same level in terms of efforts from your side also. Like the resource persons have already explained you that this is just beginning. You have to reiterate through the slides as well as material until you reach to that level of excellency, right? So it's not just about work which you are doing in the classroom. The same thing must be reflected in other aspects of lives also, right? So that we expect not to just learn quantum, but overall be a good academician also, right? And I guess that is also one of the mission aligned with quantum mission, right? Because we are not only training you as in terms of quantum computing, but also to become a good educator, right? So that is it. And I would also like to thank our participants, all the faculty members, scholars, and professionals. Thank you for your engagement as well as thoughtful discussions that contributed significantly to the success of this course. Lastly, our sincere thanks to the technical and support teams for ensuring smooth coordination and delivery of the program. So I would like to mention about our support staff, right, Dipesh ji, Geeta ji, right, and Damesh ji, right, for their continuous support. And basically, we required that for the management of WebEx as well as Canvas, so they helped very nicely. So let us carry forward this insights gained here and continue advancing the ecosystem of quantum technologies in India. And one more thing which is good, that now you are familiar with all the resource persons, and you will also get this opportunity. Utilize this in between 10-15 days in revising, and if you have any queries, you will again get to ask the questions to the same resource person. So that is, Miss, you are now very much aligned with them, so you will understand even better. So good luck. Thank you.
Thank you. Thank you, Dr. Maipal. And I would just once again thank you for all the good words that you have used. But yeah, all these efforts will be really, I would be very happy if all of you, put these things to practice and master some of these things. As I was telling Dr. Jaykumar also, from some of these courses, we want more Niveditas and more Jaykumars and more Mustafizurs to come forward, more Ashwats to come forward. And hopefully, I will continue to conduct these workshops, and I would want you to be the resource people. So please put in the efforts, and once you put the efforts, definitely I've been interacting with some of them and they have been also responding. Yes, sir, we are working hard. We will try to do that, right? So I hopefully, and IBM we were discussing today, so they are going to come up with a face-to-face program for the faculty members. So we'll come up with the schedule. We'll let you know shortly. But QT-03 is coming up, so please be ready. And whatever material has been given to you, please treasure it and please revise it. Please be in touch with it and master it. So that's what I would like to say. For those who have missed QT-01 and 02, your friends, they may be asking, so please ask them to wait patiently. We're going to put the whole thing either on NPTEL or SWAYAM and give these courses and the same certificate. Provided they do these courses and pass the quizzes, we will give them the certificates. So hopefully the course will come in 30-minute capsules. So the 2-hour lecture will be divided into 4 30-minute slots. So you will have some 20 into 4, so 80 lectures will be covered. So that's great. So hopefully those who cover those exams and they pass, they will get the certificates. We are trying to work on that. So hopefully during this summer, we'll keep it ready so people can take FT QT-01 and 02 later also. So encourage them to join QT-03 now. The videos and the slides, you can make them available to your friends. All the resource people are very gracious to share the slides. Especially handwritten notes is so precious. And you can look at the slide, you can look at the video recording while the things are being written on the screen. You can follow it so easily. We hardly find any people who are handwritten teachers. So these are the best lot here. We have all of them are handwritten teachers. They have taught while writing. Jay Kumar has typed and shown the codes, and it's all practical. So thank you so much for being with us. Hope to see all of you in QT-03. Thank you, the resource persons once again. Nivedita ma'am, shortly she'll be Dr. Nivedita, hopefully, and then Dr. Ashwath, Dr. Jay Kumar, and Dr. Mustafizur. Thank you so much, Mustafizur, taking out time from industry. He should be in teaching, actually. I have been telling him you should join academy shortly to join some IIT or ISC shortly, hopefully. But then, yeah, some people are needed in industry also. So, but taking out time from industry to be with teachers, that's great. Thank you so much. Thank you, Ashish sir. Thank you, Maipal. And thank you all. So it's time to say goodbye. We'll meet you in QT-03. Thank you. Thank you.
Bye. Bye-bye.
We'll take one snap. We'll take one snap. Yeah. We'll take a photo. Photo. नहीं स्क्रीनशॉट ले लो, प्रिंट स्क्रीन करो. Just a second. Yeah, thank you so much. Thank you for, thank you.
Thank you.
Thank you.